knowledge, like the convection chapters. So back in chapter 1 and some of these other chapters, we've used radiation. We've looked at problems that have radiation in them, right? So, but they've given us the emissivity, or they've given us the solar radiation, or they gave us the absorptivity, right? Well, in this chapter, we're going to understand how we can get that value ourselves. Just like we did with convection in those early chapters, it just gave you the convection coefficient. And now we know in chapter 6, 7, and 8 how to calculate our own, okay? And in chapter 12, we're going to figure out how to calculate our emissivity, absorptivity, and how to understand how to calculate, or how to simplify it and neglect things. So we're going to start with understanding it fully and what it's dependent upon, and then have these assumptions we can make to make the problem simpler to getting our emissivity and our absorptivity, okay? But that's the main kind of goal you'll see in this chapter 12. Okay, so don't get overwhelmed with some of these equations are bigger equations, and it's there at least to understand what's going on, okay, before we simplify. All right, so we're going to be looking at thermal radiation, right? And any matter that's above absolute zero is emitting. It has emission going on, okay? So if you're sitting at a table, that table's emitting, okay, because it's above absolute zero. Any piece in the room that you're in, it's emitting. It has thermal radiation that it's emitting, okay? But it's also absorbing, right? And this emission, though, is due to oscillations and transitions of many electrons, okay? So when we get an emission, it corresponds in heat transfer, you get a reduction in thermal energy, okay? But as I said, radiation can also be intercepted. You have that irradiation. It can now be absorbed, okay? And this increases the thermal energy. So now you have this emission, what's leaving, and you have this radiation or irradiation, what's coming in, okay? And that's what you see down here, right? We have what's leaving, and then we also have from the surroundings what's coming. The surroundings are emitting, but then that's what it's emitting is going to hit that solid, okay? And you get a net radiation heat transfer between these two, and you might have a net radiation leaving or net radiation entering, depending on which temperature is higher. Right? All right, so we have, when we're talking about emission from a gas or a semi-transparent solid or liquid, we can look at it as a volumetric phenomenon. Okay, so think about a gas. If it's emitting, you could easily more think about that as a volumetric. But if we're looking at emission from an opaque solid or liquid, so that table I'm talking about that you might be sitting at, if it's emitting off its surface, if it's glass table, then now you have some transparency there. But if it's a wood table, let's say, then you have surface phenomena. You have it is just occurring at the surface, okay? And it originates, in a very small difference within the surface. That's why we can think about it as a surface phenomenon. Okay, we have a dual nature of the radiation. Sometimes it behaves as particles, and sometimes it behaves as an electromagnetic wave. And any radiation is characterized by wavelength and frequency, which is related by speed, right? Speed, frequency, and we get our wavelengths. So we're going to hear a lot. You're going to hear me use the term wavelengths a lot in this chapter because it ends up being a dependency for radiation. All right, but before then, let's start off with the electromagnetic spectrum. right? So we have all these kind of different wavelengths here, and thermal radiation right here occurs in a little bit of the ultraviolet section right here. Not all of it, but a little bit. We have visible spectrum, so it can occur within the visible spectrum, and we have the infrared spectrum, okay? So you have these three spectrums, but it can be occurring in any of them or all of them. It really depends, okay? And so we have infrared, visible, ultraviolet. So that means you don't always see it, right? Thermal radiation. And it also then means it has a distribution. So spectral is talking about wavelengths, okay? Okay, so it could have over the spectrum, it could have a different radiation emission. So it could not be the same throughout those different wavelengths. Might be more dependent upon the infrared versus the visible and ultraviolet, or it might be higher in the ultraviolet or visible and not in the infrared. Okay, so that means we have that spectral distribution that we have to understand. Okay. All right, so going through kind of some of these terms, and we talked about these earlier in the semester. We have emissive power. So this is what's coming off of like that table is emitting, okay? If it has a temperature above absolute zero, it's emitting. So this is a radiation emitted from a surface, okay? And that's our equation. We use that, and it was introduced in chapter 1. We have irradiation. So now this is radiation incident upon a surface. This is what's coming in and hitting that surface, right? And that irradiation can be reflected, absorbed, or transmitted. Okay? If it's reflected, it hits the surface, bounces right back, right? Absorbed, it means now that energy is going into that and being absorbed by that surface. Transmitted means it's going right through it. Okay? Radiosity is now a term, is just talking about radiation leaving a surface. So any radiation that's leaving, and that comes from what's emitting, okay? Because that's what's coming from a surface right here, and it's also coming from what's reflected. Okay, so that's this portion. Emitting plus reflected. Okay. Net flux, radiated flux. So this is our net, okay, and they're using J minus G, okay? So that's our radiosity minus irradiation would be our net rate of radiation. So net leaving a surface, okay? And they've reduced it down to this, and we can reduce it. So they have radiation is J minus G, right? Where J above is E plus what's being reflected of that irradiation. And then we have minus G here. That's still being carried. And if we use and pull the G out, we would have rho minus 1, or reflectivity minus 1, I should say, times G, right? So that is going to end up being right here, as you see in this equation, that's going to end up being minus absorptivity. And I'll show that below when I get to it. That's where this change from this to this comes from. Okay. All right, so if we look at now the irradiation is coming in, some of it gets reflected, some of it gets absorbed, some of it transfers right through. Okay, so that means G is reflected, absorbed, transmitted. Reflected, absorbed, transmitted. Okay. Well, the reflected amount is just the reflectivity times G. The absorbed amount is just the absorptivity times G. And the transmitted is just the transmissivity times G. And that all is equal to G. So if I was to then cancel G out, you then have 1 reflectivity plus absorptivity plus transmissivity. And that's what you see right here. Okay, that's where the relations of those 3 parameters of a material are. Okay, if it's opaque, that means now it's not going to transmit anything. This goes away. So then 1 equals rho plus absorptivity for opaque. All right. Well, we want to get this thing I said here. Well, if we move this around, you're just going to see that negative alpha, or absorptivity, is rho minus 1, which is exactly what you see over here that we threw there. Okay, or, you could have substituted in better. It would have been alpha is 1 minus reflectivity. So if it's not getting absorbed, it's getting reflected. If it's not getting reflected, it's getting absorbed in an opaque surface or medium. All right, so now we start going into the different things we got to worry about. So if you're looking at that table I mentioned, the example, well, it basically it's emitting in all directions, that surface of the table, like a hemisphere over it, like half of a globe, right? Half of a globe that it's emitting over. Okay, so it's emitting in different directions. Okay, so that means we have a directional distribution. Okay, so that means we have to worry about directional considerations and the radiation intensity at those different directions. So it might be emitting here more than it's emitting here at different points over that hemisphere. Okay, so that's where that directional influence we have. It's a function of the direction. Okay, and we have these 2 angles, and you'll see there's a bunch. We have this one, okay, and then we have our polar angle right here. It's just introducing more of that hemisphere. So if we're looking at this being our surface on a point on our table, we're going to be integrating all the way around, so 360 or 2 pi in that direction. And then we would integrate, let's do it higher, in this direction, 90 degrees. Okay, and doing those 2 integrations over that 2 pi or 90 or pi over 2 directions, right? That's what you see right here. You're going to be integrating over that whole hemisphere. Okay, and that they look at it a little differently with this integration over this hemisphere is how we have radians for a circle, right? They created steradians for a hemisphere. Okay, and if we look at those angles over that we're integrating, that ends up just being like 2 pi steradians. Okay, so when we're talking about spectral intensity, that's the intensity of the radiation as a function of wavelengths. That's spectral, and then we could have an angle dependence. So here we have heat flux per meter squared, right? We've done heat flux watts per meter squared, right? You've seen that. Well, here they have it now with at a certain direction, we have watts per meter squared, steradians. Okay, so that shows us there's a directional dependence, right? And then if we put in our wavelength dependence that we have from looking at our electromagnetic spectrum and our figure there, we're going to now have watts per meter squared, steradians, and then our wavelengths. Okay, so that shows, you know, the directional dependence, wavelength dependence, right? So to get to watts per meter squared, we'd have to integrate over direction and then integrate over wavelengths, right? Basically to get rid of those two denominators, those two units. Okay, so one thing to look at spectral intensity, right, is the subscripts in some of these equations. So we have wavelength, and then we have emission. So wavelengths. So that's at different wavelengths, right? It has that functional dependence. And then this is telling us it's the emission part. So it's not the irradiation or radiosity. That's just the emission. Okay. Here's our, you know, direction. Right? All right, so then we have an assumption we can make to simplify. Okay, so first off, we have if this spectral intensity is independent of direction. So that means at any point around that hemisphere, that spectral intensity is the same. So it doesn't matter at what point you're at. That means it's independent of direction. There's no dependency on direction. It's not higher at one point in the direction versus the other. And that's a surface that we can call diffuse. Okay, so that's a simplification we'll make to kind of get rid of directional influence. Okay, we assume a surface is diffuse. Okay? And that's where radiation is isotropic. It's the same. Okay, so that's a big assumption we can use. All right, so here is what I talked about, is that integration. Okay, so we have spectral emissive power. It shows watts per meter squared, and then we have our wavelength unit, right? So if we that means we're going to integrate over our direction. Okay, so so that means we're integrating over the hemisphere. And then the total emissive power, which is what we saw in chapter 1, you know, that when we just said capital E, is now we integrate over all wavelengths. And that gets us the total emissive power. Okay, so integrate over the hemisphere, then integrate over the wavelength, and we get that total emissive power E, right? Well, if we're able to say a surface is diffuse, right, that's where it's isotropic, doesn't have a directional independence, it's the same at any direction. Then when we do this integration over the direction, when it's the same at any direction, we actually just get pi here, right? And if we integrate over now the wavelengths, then we just get, for total E, we get this. Okay, or total emissive power, we get this. Okay, so it simplifies it a great deal, right? We can do similar things with spectral irradiation. So you see it's wavelength and irradiation. Everything else looks the same, right? In G, right? Tells us about irradiation. But if you compare that equation at the top to this one at the top, it looks the same except for those things I just mentioned. And if you integrate over direction, then you get to now have to integrate over wavelength. And that's where you get the total irradiation. If it's diffuse, we can create equations for it that look exactly like these two here, just with the term as G and the subscript E changed to I. And again, we can do the same thing for radiosity. In radiosity, wavelength, and it's emission plus reflection, right? Again, this equation looks the same except for J, and this E plus R. Okay, where this was just E, this one was just I, and now we have E plus R. Okay, so if we integrate over direction, we get this. Integrate over wavelength, and we get this. Okay, and again, for diffuse, we can create our equations, which is J instead of I here. All right, Blackbody radiation. So this was introduced in its intensity, again in chapter 1 a lot. Okay, so the blackbody is the idealization, and it puts limits on radiation emission and absorption. Okay, and what it is that a given or prescribed temperature and wavelength, we get our ideal emitter. No surface can emit more radiation than a blackbody. And that was basically in the earlier chapters when you had an emissivity of 1. That means you have a blackbody. Or if you had 0.5, it was 50% of what the ideal emitter would be. Okay. Blackbody is a diffuse emitter, so it's the same in different directions, so it doesn't have a directional dependence, right? It's diffuse. And then it's also absorbs all incident radiation, so it's the ideal absorber. And that was the absorptivity when it was 1 in the earlier chapters. Okay, so it's the ideal emitter and ideal absorber. One example of this blackbody is an isothermal cavity, right? If you have this small kind of aperture here, and you have this cavity, and you have some incident radiation coming in, it's just basically going to bounce around in there until it gets absorbed. It doesn't matter if that surface inside here is highly reflective or not. It's just going to bounce around because you're saying this little pinhole is so small, it's not going to hit it, and it's just going to bounce around until it gets absorbed, right? But the same thing happens for emission. Is because of this small hole, it's basically going to get all these things getting this nice diffuse emission coming out of it, any parts that actually get emitted out of that little aperture there. Well, okay. All right, so then we want to know how to quantify that emission or the emissive power for a blackbody, okay? Because it has that spectral distribution, right? All right, so what we see here is the equation that defines the emissive power. Right, so this is the emissive power of a black body. Okay, and it has wavelength. It's a function of in temperature. All right, and we see the equation that defines it. Okay, has these constants for it. And if we put in that equation right here, 50 degrees Kelvin, and draw our curve, we're going to get this curve right here. Okay, because this is all our wavelengths. Here's our spectral emissive power, right? 300 Kelvin, which is what your table is, you're going to get this emissive power. That's what your table, the example of your table emitting radiation, that's what the curve is off of the table, right? And then if you keep making these lines, we can go all the way up to 5,800 Kelvin, and that's the sun entering the Earth's atmosphere. Okay, and we get that curve. Okay, so that's the emissive power as a function of wavelength now at a given temperature, right? Because this is 50 Kelvin, 300, 5,800. And this is a very important figure because it tells you, depending upon temperature, so let's say that your table, or if we're solving for a surface temperature of something, we did that a lot, right? Even chapter 1. It now tells us, is that surface going to be emitting you're going to have a lot of emission in the high wavelengths, low wavelengths, right? Depending upon its temperature, right? The sun has a very high temperature, so we're going to get those low wavelengths, right? Low temperature, you get these high wavelengths, right? You can also get our max wavelength that it's emitting at. So that's this point right here, 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 and here. Now, if we were to integrate, say we integrate this over the wavelength. Okay, do that here. We can integrate over the wavelengths. So if we integrate that function, right, what you see right here, but keep the temperature term still in there. So we integrate over all the wavelengths, we're going to get Stefan-Boltzmann's constant times temperature to the fourth. So that's the equation we've been using. Okay, and that's where it comes from. And this Stefan-Boltzmann's law is where that Stefan-Boltzmann's constant comes from that we've been using. Okay, it comes from that integration of this equation. Just leaving temperature influence in there and integrating everything else out over all those wavelengths. All right, so that becomes important, and we're going to look, this section becomes really important in the examples and the problems we're going to do, okay, and understanding it. And I'm going to actually stop there because this is where I ended in the other class. Do you have any questions? We'll get through these slides next class and work on our examples in the next class or two. Okay. And then there's no questions. Then that's it for today. If you have any questions that you want to meet with me directly, you can go ahead and email me. Again, I posted the solutions to the exam. If you have any questions, please don't hesitate to contact me, and we can move from there. Okay.
Okay, thank you.
Yep.
All right, thank you, Professor.